Hello, in this video I want to talk about nuclear decay. Nuclear decay. Let me start with the definition of nuclear decay. It is also called radioactive decay or radioactivity. Radioactivity. So now this is a definition which I found on Wikipedia. It's described as a process by which a nucleus of an unstable atom loses energy by emitting particles of ionizing radiation. And this could mean say for example alpha, beta or gamma particles. So this is how it can be described: nuclear decay, radioactive decay or radioactivity. Now let's look at a more concrete example. Let's say I have a little radioactive material, say a small piece of material called cobalt 60. Cobalt 60. Now when we call an element, say like cobalt with a number next to it, cobalt 60, what it means is that we are talking about specifically the isotope of the cobalt atom, in which its mass number, or in which the total number of protons and neutrons is 60. So that's what it means when we say cobalt 60. Okay, so let's say I have a small lump of this cobalt. So this is supposed to be a lump of this material. It's not an atom. So let's say I have a small amount, like maybe 0.1 gram. Okay. Now, cobalt 60 decays by emitting gamma radiation. So let's say it gives out this gamma radiation. Now this gamma radiation is given out, it's an electromagnetic radiation, so it will be given out as photons. So it would be emitting, each time an atom decays, it emits a photon, and when another atom decays, it emits another photon. Okay, so we have these gamma photons. Okay, and this can be detected by an instrument called Geiger. Let's see. Geiger Mueller counter. Okay, so it's something that goes click click click, where each time it gives a clicking sound each time it detects a particle, a radioactive particle like alpha, beta or gamma radiation coming into it. Okay, and the one of the way to measure radioactive material is to measure how many particles are emitted by the material, or at least detected by the counter every second or every minute. Now this quantity is called the activity. So if I write this down, activity is equal to the number of particles emitted per unit time. To be precise, number of radioactive particles, which can be alpha, beta, or gamma particles. Okay. Of course, if we are just using a Geiger Mueller counter on one side of the sample, it wouldn't actually detect all the particles that are coming out. Particles will be coming out in all sorts of random directions. Okay. So, but for now, let's just say that suppose that the Geiger Mueller counter is measuring the activity of this radioactive sample, right? Or based on its measurement, we can estimate the total amounts coming out in all directions. So from this measurement, suppose that we think about measuring this at regular intervals. Okay. Now we'll find that let's say what we do is we measure it for perhaps we measure it every 1 minute. Right? Let's say we get the counter to count how many particles are coming out every minute. So we plot the graph. Alright, we plot the graph of this number of particles per minute. Imagine doing that. So we plot the graph against time. Let's say the time in maybe minutes. Okay, maybe not minutes. Just let's say the particles detected per minute. And suppose that we plot the graph of this as time passes. Now what you would find if you do that is that as time passes, the number of particles emitted per minute would decrease. It would actually decrease. Okay, and if you're very patient and you do this for in the case of cobalt 60, if you do this for a number of years, well, maybe you don't have to do it every minute. You can do it every month, perhaps, or even every year. Right? Just come back once a year and take a measurement. What you'll find is that when you plot the graph, you get a graph that looks like this. It doesn't actually go down in a straight line. Okay, well, it would go down because the cobalt, more and more of the cobalt 60 has decayed, and those atoms that have emitted gamma photons would not emit anymore. So only the remaining cobalt 60 atoms would continue to emit gamma photons. So there will be fewer and fewer cobalt 60 atoms or nuclides that can emit gamma photons as time goes by. So as time goes by, we would expect therefore that the activity would somehow decrease, and indeed that's what we would observe. And we would also expect that if we wait long enough, all of the cobalt 60 nuclides would have emitted the gamma photons, and by that time, when all of them have emitted, there would be no more atoms that can emit, and then the activity would stop. So eventually we should have a graph that comes all the way down to 0. Now, but if you actually carry out these experiments, you'll find that the graph doesn't actually go down in a straight line. It does go down, but it goes down like that. It sort of, starts curving, and it just gets closer and closer to 0, but it never actually seemed to reach exactly 0. Alright, unless perhaps if you wait for an extremely long time until the Geiger-Mueller counter cannot detect any particles coming out anymore. Okay, but if you wait for many years, you'll find a graph that looks like this. Right. Now, that's one thing. Now, the other thing is that there is something unusual or something special about this graph. Now, if you're actually, so patient and you're actually using Cobalt 60 for these measurements, what you'll find is this. You'll find that after about 5 years, maybe just a little bit more, okay. Now let's say the time is in years. Okay, so it takes a long time. After about 5 years, what you'll find is that this activity, let's say it starts with the starting value is particles per minute. Not sure exactly how much it is. I'll just call it A0, or just pick a random number like maybe 20. Okay, so you find that after 5 years, it would have come down by about half. So after 5 years, the activity would have come down by about half to say 10. Okay, and then after another 5 years, it would come down by about half again from what from the activity from the 5-year time. So it'll come down to 5. Okay, and after another 5 years, okay, it will come down by half again. So it has this very special behavior. Each time after the same period of time, it can come down by half. Now this time during which it comes down by half has a name. It's called a half-life. And this is one of the special behavior, and it shows it behaves in a similar way for all other kinds of radioactive materials. Right? Even if they might have a different activity at the start, they might have a different half-life, but for all radioactive materials, they will show this feature when you plot the graph that after a time when half of the activity is reached, you'll find that if you wait for the same amount of time, the activity will come down by half again, and then after the same period of time, it will come down by half yet again. Okay, in the next video, I'll explain a bit more about why this is the case.